Recently, I was chopping firewood and the axe went so deeply into the ground that it cut the cable. Apparently, I'm stronger than I look. I think we can all agree that the cable should be buried more deeply. Eventually, the cable guy came out and ran a new line from the street around the patio, connect to the cable box over there. I paid attention closely to where that is, so that now I know to chop firewood over there. I'm Professor Mark Hinders, Applied Science Department at William & Mary. So even if I wanted to cut the cord so I wouldn't have to pay the cable company for all those channels I don't watch, I would still need the coax coming in from the street to connect to my Wi-Fi router. A break in a cable is a fairly simple thing to detect. The way the cable company does that is they send a little voltage pulse down the cable from the street, and it will reflect back from any breaks in the cable. This technique is called time domain reflectometry. And breaks in cables are quite simple to find. It tells you, you have to sort of know where the cable goes, but it will tell you how far along the cable the break is, because the speed the voltage propagates in a coax or any other type of wiring is understood. So time delay allows you to convert with that speed of propagation into distance. And then you can go and dig at exactly the right place. In my case, I made note of where the axe sliced the ground, so we knew where the cable was. The more interesting and maddening kinds of flaws to find are ones where it's an intermittent flaw. Right? Maybe some wires in some situation have been rubbing against each other, or it's just started to fail and the fault comes and goes. So time domain reflectometry can still find those types of flaws, the intermittent types of flaws, if you can analyze the waveforms that come back in the TDR signals to pick out the more subtle peaks that are related to intermittent wiring flaws. Right? What we do is we take that time domain signal and perform a mathematical operation on it called a wavelet transform, and then we get a time scale image, and the way that we render that is sort of a black and white contour plot, and those quite often look like fingerprints, so we call them wavelet fingerprints. And then the idea is to find shapes in the fingerprints that correspond to the flaws that you're after, and then you can search the images for those shapes, and the position of the image in the time scale image allows you to identify how far along the wire the fault is. So what we find is that different types of flaws give different shapes. Let me show you an example. In a coax chafing example, what we found is that the TDR peak corresponding to the flaw gave a triangular shaped image. So if you look at this set of images, here what we've done is sequentially increase the severity of the chafing flaw. And what you see is that triangular feature gets more and more ridges in it as the flaw gets more severe. So we can search for triangular shaped images in the wavelet fingerprints, count the number of ridges, and that provides a quantitative way to characterize the severity of the flaw. There's a lot of flexibility in this. There's many mother wavelets that can be used to form the wavelet fingerprints. You also have a lot of flexibility in the wavelet fingerprint about the parameters that you choose to render them. And so what you can do is explore a bit with a new data set, the different parameter settings and mother wavelets and amount of denoising and things like that that are helpful to highlight the flaw signatures of the flaws that you care about. And so what we did was we wrote an easy-to-use MATLAB GUI that allows us to very easily read in flaw TDR, in this case TDR signals, and then explore sort of interactively what combinations of things are promising for automatically identifying the flaw that we care about. And the eye is very good at picking out features in these kinds of images, think reading messy handwriting. And so we can do this interactively at first, and then what we do is we identify features, form them into feature vectors, and then we can do formal machine learning to identify automatically the flaws that we care about. So having your cable go out is one thing, but in aviation applications, this can be a serious issue, especially intermittent flaws in wiring systems in aircraft can have a serious impact on safety, of course, but also on readiness. So we did a project applying these techniques to wiring harnesses in F-18s. This was for the US Navy, NavAir. And what you're going to see here is some TDR signals for wiring harnesses in F-18s. And worked pretty well. The situation that you're really after is to put brains on board the aircraft so that it doesn't just give you an indication that there is a wiring fault. Instead, what you would like the onboard system to do is automatically interpret the signals that come back from the wiring fault, send the TDR signal down the suspect part of the wiring harness, analyze the reflections that come back, do some machine learning on them via perhaps Wavelet Fingerprint, so that the aircraft can alert the maintenance personnel that not just that there is a problem somewhere, but that the problem is in a particular place, in a particular harness, go there, execute the repair, or maybe there's an issue, but it doesn't need to be repaired right away. That kind of intelligence can now be built into very compact systems that can be installed on board things like aircraft. It's amazing how much wiring there is inside a modern aircraft. Next time you're flying commercially, imagine all the wiring it takes to feed all those video screens and whatnot. And so the better techniques to automatically identify and characterize incipient or intermittent flaws in wiring is very much of interest in aviation. It's also of interest if you're trying to watch something on television and your cable goes out, because now it's not just your cable, it's also your internet. And there's probably nothing good on now, but I'm going to check and see. I'm Professor Mark Hinders, Applied Science Department at William & Mary, as.wm.edu.